We're now going to consider an application of both volumes of revolution and arc length. In order to compute the surface area of a solid of revolution, you'll need both the idea of a volume of revolution and the formula for arc length. We combine these two techniques to find the surface area of a solid created by revolving about an axis. We'll revolve about the x-axis or the y-axis. We're going to think about the surface area as the bare minimum amount of paint needed to barely cover the surface exactly one time, or you could think of it as the amount of wrapping paper needed to wrap the solid without any gaps and no overlaps. In other words, we're going to take a curve or something that looks like this, as you can see here in this picture, and we're going to revolve it about an axis. In this case, it was revolved about the x-axis. The question is, now that I have this solid in three-dimensional space, how much paint would it take to paint the thing? That's what we're trying to find. How do we do this? Well, we do it the way we've done it many times before. We're going to cut up the interval from A to B, from where the curve started to where the curve ended when we revolved it, and we're going to approximate the surface area by calculating the surface area on a simpler shape. The simpler shape that we need is called a frustum. The frustum looks like this. When you're taking the frustum of a right cone, it's basically taking a right cone and chopping off the pointy end of it, and that gives you something that looks like this. To my mind, these often look like some of the yogurt cups that you see in the grocery store. They have this particular shape. Now what we want to do is slice the frustum along one edge and peel it open to get this. We've got a frustum of a right cone now. If we let R1 and R2 be the radii of the wide end and the narrow end respectively, and let L be the slant height, then we get the following picture. We have R1 being the radii of the wider end, and remember, that's looking at this end down here, the base of what would be the yogurt cup. Then we let R2 be the radius of the inner part, or the top of the yogurt cup. We let L be the length of the slanted side of the yogurt cup, or the frustum. Now we want to rotate it counterclockwise 90 degrees, in other words, turn it on its edge. When we look at it this way, we can see that R2 is the function value at some point to the left of where the function value gives us R1, which is at x sub k. From geometry, there's a formula that will give us the surface area of the frustum as basically pi times R1 plus R2 times L. In other words, we add the two radii together, we multiply by the slanted edge length, and then we multiply by pi. That will give us the surface area of this little piece right here that can be coiled together into a loop to form the frustum. This means that it goes all the way around this way. Note this does not include the surface area of the top or the bottom, which of course are circles. This is simply the side edges of the yogurt cup, and that's really all we want. We use this formula right here to find the surface area of the solid of revolution using the arc length formula to replace L, since this distance right here is basically, well, it's arc length. So what we have in our formula then is pi times f of x sub k minus 1 to get the value at R2, the short end or the narrower end of the frustum, plus f of x sub k, which gives us R1, or the wider end of the frustum, multiplied by L, where L is given by the arc length formula, the radical of 1 plus the derivative at some x sub k star quantity squared times delta x. Then we can apply the intermediate value theorem, since f is continuous, to say that there must be some point x sub k double star on that subinterval that is exactly the value of the average of the two radii. Well, that's because the intermediate value has to be taking place somewhere between the two. So somewhere in there, there is an x sub k double star on that subinterval where its value is the average of R1 and R2. That means add R1 and R2 together and divide by 2. This will give us f of x sub k double star, and that's somewhere on that interval between x sub k minus 1 and x sub k. When we put this into the formula, this means that the distance f of x sub k minus 1 plus f of x sub k, which is really the radii added together, becomes double that length. Since half of the sum of the radii is equal to that, then the full sum becomes 2 times that value. Now we can replace this in our formula. 2 times f of x sub k double star replaces what we have here, and then we have L being replaced by the arc length formula, which is the radical times the delta x. Pi is a constant which is just coming along. In this case, then, we want to add all of them together, which is a Riemann sum, and then we take the limit as the number of cuts goes to infinity. This also means that our width, delta x, is going towards 0. This gives us the definition of the definite integral from a to b of 2 pi f of x times the arc length formula, the radical of 1 plus f prime of x quantity squared dx. This tells us, since the f of x value is equal to y, that we have the formula 2 pi y times arc length. In other words, 2 pi y arc length is the formula for the exact surface area. Yes, there's a bit of hand waving in there. We do need to prove that x sub k double star goes to the x value as n goes to infinity. It does, however, because of our requirement for smoothness in the arc length formula. Because it's required in the arc length formula, smoothness is also required for the surface area formula. There's another similar formula for integrating with respect to y instead. Let's take a look now at our theorem. Let f of x be a non-negative, smooth function over the interval from a to b. Remember, smooth means that we have a derivative that is continuous. Then the surface area of the surface of revolution formed by revolving the graph of f of x about the x-axis is given by the integral from a to b of 2 pi y times the arc length formula. Now, we can think of this in a different way if we're going to write it as a function of y instead. If we let g of y be a non-negative smooth function over the interval from c to d, where c to d are y values, then the surface area of that surface of revolution will be formed by revolving the graph of g of y about the y-axis instead, and it's given by the formula, the integral from c to d of 2 pi x times the arc length formula expressed in terms of the y variable instead. You can think of these formulas as basically being circumference times arc length. In other words, 2 pi r arc length. Since the x value, when revolved around the y-axis, is the radius of what's being revolved, and the y value, when revolved about the x-axis, is the radius of what's being revolved. This makes it 2 pi r arc length. Let's now take a look at an example. In example 7, we want to find the surface area of the solid produced by revolving the simple graph y equal the square root of x about the x-axis, but only the portion between 1 and 4. Here's a graph of the square root of x between 0 and 6. We want to take the portion between 1 and 4 and revolve it about the x-axis. You can see the picture produced here of the solid of revolution produced in Calc Plot 3D. Let's write down the formula that we need to compute the surface area. Since we're rotating about the x-axis, that means that our strips are going to be running vertically, and our radius is given by the height of the strip, or the length of the strip. Since the length is given by the y value on our curve, square root of x, and that gives us the radius, r is equal to the square root of x. Our formula is the integral from a to b of 2 pi times the y value times the square root of 1 plus f prime of x quantity squared dx. Remember that this part at the back is basically the arc length formula. This means that we'll need to find f prime of x, square it, add 1 to it, and put it under the radical. However, we can also think of the front part as the circumference of this circle, which is 2 pi r times the arc length. To replace the r, we'll need to replace the y in the formula with the square root of x, since our differential is dx. Go ahead and pause the video here, work out the algebra and the calculus, then turn the video back on to compare your answer to mine. Recall that our function is given by the square root of x, so the derivative is 1 over 2 the square root. Then we square it to get 1 over 4x. Add 1 to get 1 plus 1 over 4x. This goes under the radical. Then we are multiplying by 2 pi times the y value, since we are rotating about the x-axis and our differential is dx. We replace the y, since it represents the radius of what we're revolving, with the square root of x. Notice that our limits of integration correspond to the region over which we are revolving, from x equal 1 to x equal 4. Putting it together then, we have the integral from 1 to 4 of 2 pi square root of x times the quantity 1 plus 1 over 4x. We can get a common denominator here and rewrite the 1 as 4x over 4x and leave the other as 1 over 4x. The advantage to this is it allows us to separate the 4x in the denominator from the numerator part of the radical. Remember that when you have multiplication and division, you are allowed to split the radical. When you have addition and subtraction, you are not allowed to split the radical. We split the radical across the division to get the square root of 4x plus 1 in the numerator and the square root of 4x in the denominator. The square root of 4 becomes a 2, and that will leave us with the square root of x to cancel with the square root of x. This square root of x came from the y value. This square root of x came from underneath the radical inside the arc length formula. These cancel. The square root of 4 gives us a 2, and the 2 cancels with the 2 that's out here, which just leaves pi as our coefficient factor. Then we have the radical of 4x plus 1, so we can do a U substitution. By completing the U substitution, note that we write the limits of integration as x equal values, and once we're done, we can plug in the limits of integration. After plugging in the limits of integration, we get an exact value of pi over 6 times 17 to the 3/2 power minus 5 to the 3/2 power. This works out to be about 30.846, and this is square units. This is the amount of paint you would need in order to paint it. In other words, this is the square footage of that solid that we got by revolving that curve around the x-axis. Let's take a look now at example 8. In example 8, we want to find the surface area of the solid produced by revolving the curve x equal y squared about the y-axis over the interval from 0 to 9. First, note that this interval is the x interval from 0 to 9, as can be seen here in the picture, where the x is going from 0 to 9 in blue. Also notice that the graph of x equal y squared is a right opening parabola. This means that in order to integrate, we're going to have to adjust these values to be y values instead. Look at the picture here. See how the picture becomes sort of like a funnel coming down towards the center. If you think about the shape is sort of like one of those coin catchers that you see in shopping malls, where you can donate money to various causes by putting money in a slot along the edge and watching it go around and around and around and then down the funnel. Let's take a look at the Calc Plot 3D picture to get a better idea of this solid of revolution. In Calc Plot 3D, I set my interval for x to be between -9 and 12 with tick marks every 3 so that I could see that it was going out to the value of 9. I also set my y values to go from -2 to 4, since I knew that an x value of 9 would correspond to a y value of 3, and an x value of 0 would correspond to a y value of 0. Now let's take a look down here by closing up that screen there. You can see that this is the shape that is being revolved, and it's being revolved around the y-axis. When we look at our equation down here, how do we know that's what's happening? We have the equation square root of x, and the bottom of it is given by the x-axis, y of x equal to 0. Our interval here goes from x equals 0 to x equals 9, but our axis of revolution is x equals 0, which is the y-axis. The region is already rotated, but we can unrotate the region so that we can come back and see how it is coming directly from this graph that we see right here and also in the 2D image here. We're taking it and we're rotating it about the y-axis. Can you see the funnel shape that is developing as we rotate around here in the center, coming down to where it reaches the point of the vertex of the parabola at the origin? Now we continue rotating until we can see it all the way around. Let's tilt it sideways so we can see the shape of the funnel there and the flat bottom on the bottom. This is basically what we're looking at. We want to know what the surface area of this volume of revolution is. In other words, how much paint do I need to paint this whole thing, including this funnel shape as it comes down here? Let's write down the equation that we need in order to compute the surface area when we're revolving about the y-axis. The equation we need is the definite integral from y equals c to y equals d of 2 pi x times the square root of 1 plus the derivative with respect to y, quantity squared, all under a radical dx. Recall that this back part is the arc length, and this is basically 2 pi times the radius. What do we mean by the radius? Well, in our picture up here, we are rotating around the y-axis this direction. And if we're rotating around the y-axis, that means that we're taking our shapes here, and if we're looking at the shell method, that means that this distance right here is basically the radius r. That distance is the x value on the curve. And the x value on our curve is given by y squared. Let's go ahead now and work out converting our values for 0 to 9 to being y values. To convert our values from x values in 0 to 9 to y values, we need to think about what we're looking at. In the picture, it's marked off in blue, which clearly means we want the upper part. Since this is a symmetric graph about this axis, it wouldn't matter whether we took the upper or the lower to revolve. We would get the same amount of surface area because we would have the same shape, just upside down. In this case, we want the upper part. So we're looking at taking the equation x equal to y squared and letting x be equal to 0. This gives us 0 is y squared, or y is equal to 0. So we will choose y to start at 0. Then we replace the x with the 9, and that gives us 9 equals y squared. This again gives us the choice of positive or negative 3, but based on the picture, we want the upper part, which is positive 3. Again, because the curve is symmetric about the x-axis, taking either the upper portion or the lower portion and rotating about the y-axis would still produce the same amount of surface area. Let's now take a look at completing the integral and evaluating our surface area. Pause the video here, compute the different pieces, work out the algebra and the calculus, then turn the video back on and compare your answer to mine. The next thing we want to deal with is the arc length part of the surface area formula. We have x equal to y squared, so when we take the derivative with respect to y, remember that we are getting dg dy here, we get 2y. Then we square it to get 4y squared and add 1 to get 1 plus 4y squared. This goes underneath the radical in our formula. The formula is 2 pi times the radius, and the radius is the x value on the curve. But the curve is x equal y squared, so we can replace the x with y squared. We need to do this since the differential is dy and we need all our variables in the integrand to be y values. This gives us 2 pi y squared times the radical 1 plus 4y squared dy. We change our limits of integration from x values to y values to correspond with the differential dy. This is a very difficult integral to evaluate by hand, so you can use a table or an online integral calculator to find the value of it. Here's the value that you see down here. Then we plug in the limits of integration from 0 to 3 to get this exact value here, which is approximately 261.318 square units of paint to paint that funnel shape that you see that looks like a coin catcher in a shopping mall. This is the end of the video covering surface area. In the next video, we'll be taking a look at work applications, which are completely different from arc length and surface area.